I'm still skeptical, though, that they're going to open things up, because it would be very unlike anything the governor's done so far. And I don't know how you justify 4 days later, after saying nobody's going to bully you, that you get bullied into doing it, I guess. You either look weak or you look like you're indecisive. I'm talking to you, Brett. All right. Yeah, don't show her that until after she makes the decision. So, questions. So today I mostly want to talk about counting. But I wanted to see, are there any homework questions that people have? Anything? You could be asking something that I'm going to talk about anyway, but I like to see what people are struggling with the most. Yes.
So number 24 from the international version,
The
the
same?
one with like the cards, and if you had like the 4 consecutive aces.
Yeah. Okay. All right. So counting. So this is number. I'm trying to 4 consecutive aces. Yeah. So that's number 20 in the U.S. edition. 20, which you called it number what?
24.
24. Okay. All right. So I'm going to talk in general about counting, and then we'll get to this one also, just to make sure that we have all of the terms that we want for this class. So when it comes to counting, so far we have something called the multiplication principle. Right? The multiplication principle, which said what? What was the basic idea of the multiplication principle? If they were all that easy, right? Because they get a little bit more complicated than this. But what was the idea of the multiplication principle? Yep.
Then if there's like a certain number of runs that have a certain amount of possibilities, you just multiply like for each spot the like how many different options there are.
Yeah, if I have these 2 experiments or a certain number of experiments, right? And experiment 1 has, n outcomes, and then experiment 2 has m outcomes. And then I create this sort of super experiment that consists of these 2 experiments, crammed together. So I could, I could roll a die, and then I could roll a second die, right? Or, there's a lot of different contexts in which I could. I think the book gives some examples. I could reach into my closet, I could pull out a shirt, and then I could pull out a pair of pants at random. Which is generally how I want to dress myself. I don't care if they line up or not, right? But if one were to do that, then and the experiments would be, how many different possible outcomes are there? And the answer would be together. There would be n times n, right? Multiply those 2 things together. Okay, if we create this bigger experiment, and it's not just for 2 things; it'll be true for any number of things that we would want to look at. Okay, so that's the multiplication principle. And so what's new in this next part of this next section is something called permutations and something called combinations. And we could spend most of a semester talking about how to count things. And one of the reasons I've switched books this year is because you can really get bogged down in counting things because it gets kind of complicated and there's a lot of special cases. And so we're going to go through counting, but we're going to stay a little more focused on the type of counting that we need to do for probability. Right? So that'll be the idea here. But all of them sort of break down to permutations and combinations. They all break down to multiplication principles. So here's the idea. So we'll come back. By the way, with 20, we're going to use combinations. So while we're going through this, you can sort of think about how, well, combinations? I don't actually have to go back and think about this one for a second when we get back to it. We may want to do it a different way. Okay. So, permutations. Okay. So let's just say I have a group. Let me put these between the 2. Because actually both of these are going to start off the same and then something's going to change. So I have a group of n objects, and from that group of n objects, I will select, or I will sample of r objects without replacement. That's true in both permutations and combinations. So it's a very particular situation here. And the difference will be with permutations, order matters. And with combinations, order does not matter. Right, and when I say order doesn't matter, right, order does not matter, either order doesn't matter or I don't want it to matter, right, if it works out better for me. Okay. There are certain types of questions I could make order matter or order not matter, and I just have to figure out what's the easiest thing to do. Okay. So, that's the idea. So let's give ourselves a particular example. I'll just use the same one I used before. Let's see, I had 10 books. I have 10 books. So everyone moved here, you have boxes full of books, I'm sure. And let's just say in your dorm room, you have this shelf, and you can only actually fit 4 books on that shelf. And unfortunately, then I suppose the other 6 books are going to stay in the box for now. And let's say, okay, you have these 10 books. I mean, you're gonna pull 4 of them out of the box, and you're gonna put them on the shelf. And let's say you're gonna put them on the shelf in the way that order matters. Okay. That, you know, the fact that you have one book in the first slot and then another one then, right, is different than if you had the same 4 books up there, but the order was different. Okay. Then the question would be, well, how many ways are there for that to occur? And there's a couple of ways to think about it. I could just think about this as a multiplication principle question. I could just think of the 4 slots that I have on my shelf, and then how many do I have, how many options, how many outcomes for picking that first book? 10. How many options are there, how many outcomes for the second book? 9, and then 8, and then, right? And that's what I mean about without replacement, that when I pull something out of there, I don't put it back into the box when I go to select the second thing. Right? So every time I draw something out of there, then the size of the group decreases by 1. And that's what's happening here. So I get this 10 times 9 times 8 times 7. Do I remember what it was before? I can figure that out pretty quickly. 90 times 56 is going to be 5,040 different ways that I could take from a group of 10 distinct books, different, right? If you have 2 calculus books, that's going to change things a little bit, right? 2 exactly the same looking calculus books, that could change things. But if I have these 10 distinct books and I want to put the 4 on the shelf, and I care about the order in which I put them on the shelf, it's some sort of signal to everyone else what's important to me. I don't know why you care, but then there are 5,040 different ways for that to occur. Okay. This is also thought of, right, since it's 10, we have 10 things and we want to select 4 of them, and order matters. The book doesn't use this notation, but there's not a standard notation for such things, but I could write it this way, that I have these 10 objects and I want to select 4 of them, and the P here, permutation, means order matters. And there's a couple of ways I could think about this or write this. Here's one way I could think about this. Okay? It's 10 times 9 times 8 times 7, which is really, let's go over here for a second. If I just had the 10 books, and I want to arrange all of them, right, all 10 books, how many different ways are there of that happening?
10 factorial.
Yeah, 10 there are, now I have the 10 slots, and I have 10, 9, 8, 7, 6, 5, 4, 3, 2, there's really no choice by the time I get to the last book, right? So it's 10 times 9 times 8, and that we use this notation with an exclamation point, and we call it factorial. And anytime you see that factorial, it just means either start with 1 and go and add or multiply all of the integers, the natural numbers, up to that, right? Or start with this and keep going down 1 until you get down to 1. But if I had all 10 books and I had room on the shelf for all 10 books, and I want to know how many different ways could I order those in a way such that order matters, it would be 10 factorial. And then, I mean, essentially I'm doing the same thing here, only I'm stopping at some point, depending on how many I could fit on there. And so I could think about this as a 10 factorial divided by, and then I'm getting rid of all the 6 times 5 times 4 times 3 times, right? So I'm getting rid of the, I'm dividing by a 6 factorial to cancel those out, okay? Which is, if I want to write it this way, 10 factorial divided by 10 minus 4 factorial. Okay. If I want to know where that 6 came from, it came from the 10 minus 4 books that didn't get put on the shelf. Okay. So a permutation, I can strictly think of that as a multiplication, but that's why it's easier than a combination. I can strictly think of that pretty much every context as a multiplication principle question, right? Where I could just think about how many slots do I have, okay, how many choices do I have for one? The only thing about a permutation is very specifically, every time I draw something out, the size of my group goes down 1, and then I have one fewer thing to draw things out, and so these numbers generally are decreasing over. Okay. But if I want to, I can sort of train myself to think, oh yeah, that's a group of n objects, I'm going to select r at a time without replacement, and the order matters, right? I'm going to have, in general, p of n r, right? Which would be n factorial over n minus r factorial, right? The number of ways I could line everything up divided by the order that would be attached to those things that don't end up going there. Okay. In this case, there were 6 things that don't end up going on the shelf. Alright, so that's permutations. We don't use permutations nearly as much as combinations in probability. I mean, there's plenty of things that we can count with permutations, and there's certain reasons we care about permutations. And they might come up on occasion within probability, but more often than not, combinations are what we're interested in. So what's a combination? It's the exact same thing in which order does not matter. So I have these 10 books. Right? I still only have space for 4 books on the shelf. Right? If order does not matter, what that's telling me is I don't care that I have the books in a particular order on the shelf. I only care that there are these 4 books. And maybe that's what I should care about, because when it comes to it, if I need one of those books, any one of these 10 books, the question is it on the shelf or do I have to go back into the box to get it? Right? So let's just say that, I'm not I don't need things to line up perfectly, I don't need them to be in any certain order because I'm signaling to people that, my physics class is more important than this, I don't need to do, I don't know if anyone does that, but I don't need them in a particular order. I only need them to be on the shelf or back in the box. Okay? And so in this particular case, I could have books, I'm just going to call them A, B, C, and D, right, would be the 4 books that are on the shelf. And over here, right, A, B, C, D would be different than B, A, C, D, which would be different than D, C, B, A, which would be different than all the other different ways that we could order those things. Whereas over here with the combination, I only care that these are there together versus not there together, right? I mean, if I see this one, it means the same thing as that one, it means the same thing as that one. It means the same thing as any other reordering of those 4 books there. And that those things, while they're all the same, are then different than A, B, C, F, for instance, right? compared to F, C, B, A, F, A, A, C, B, and so on and so forth, right? That in permutations, these are all different, but in combinations, right, I still have the same 4 books, A, B, C, and F, that are on the shelf, and so that's the difference over here. So now the question is, how many ways are there of just putting those books on the shelf and not caring about the order? And if you think about it, right, I could put them up there and care about the order, and I could have my 10P4, right? That's what it would look like if I cared about the order, right? Which would be my, 10 times 9 times 8, right? There's, I guess it was 540 different ways of doing it. But now, something's going to change here, so something's going to change. I'm going to deal with combinations. This is the notation we would usually use, there's a couple of notations. Here's one of them that would go along with our permutation notation. The book, and you'll see it just as likely, a 10 and a 4, almost looks like a fraction, but there's no, horizontal line in there, right? And when we call that 10 choose 4. And 10 choose 4 means choosing without order. If you ever use the word choose, you're telling people you do not care about order. By the way, I erased my equal sign here. I don't want to write something that's incorrect, because these two things are not equal to each other. So that would be the answer. And so then the question would be, how do I adjust this number for the fact that now I don't care, I don't want to call these things different things. Because obviously I have too many things, because when I write down 5040, when I write down 10 times 9 times 8 times 7, I'm saying this is different than this, is just different than this, which is different than how many other things. And now I don't want to say those things are different. So it's really a question of how many ways could I reorder these things, which over in this grouping would all just be the same thing. A, B, C, D. How many different ways can I reorder A, B, C, D?
4 factorial.
4 factorial, right? I have these 4 slots. Right? Think of it as a multiplication, right? One of them goes in the first slot, one of 4. Right? Now one of 3 goes in the second slot, whichever one ends up there, right? Then one of 2 goes in the third slot, and then there's only the 1 left for the last slot, right? 4 factorial. Okay. I have 4 objects, and I'm going to select 4 of them, and I'm going to care about the order, right? It means the same thing. Right? Same thing right there. It's still going to give me the 4 factorial. Okay. So over here, there are these 4 factorial, 1 times 2 times 3 times 4 is 24. There are these 24 things that are identical. I'm going to call now identical to each other. And that's true for A, B, C, D if I'm working with those, as opposed to if I'm working with A, B, C, F, or if I'm working with D, E, C, K, or if I'm working, whatever letters I'm working with, every single one of them has 24 things from this original that are now going to say all of those things are the same. So my answer is, how many are there here if I don't care about order? I need to divide by those 4 factorial, those 24 things that are now no longer the same. Now no longer going to think about as the same. Right. So that would be divide by 4 factorial. Why? Because I'm trying to get rid of the idea that this and this and this and the other, 21 things that I could write down on that list are all really just the same thing for this type of question as opposed to this type of question. And now I can put my equal sign because that's what happens with these combinations. And just to sort of think ahead, anytime I divide by a factorial, I'm really saying somehow I don't care about the order in which things appeared. every time I divide by a factorial, that's probably what I'm doing. So here I had these 4 things and I divide by 4 factorial because I no longer care about the order these 4 things were selected. And that number is divided by 24, 210. Now, if it's just a question of which 4 books do I have up there, there are now 210, not the order in which they appear, but which 4 books are there. There are now 210 different ways I can think about that. Okay. And so you can probably see, combinations many times will be nicer because these numbers are significantly smaller than these numbers over here. And if I'm thinking about the different ways in which something could happen, sometimes fewer choices is nicer. I mean, sometimes you need more choices to answer a question, but sometimes fewer choices, if you can get away with it, is going to be nicer. Okay. Now, here's another way to think about this. Okay. So, and here's another way to think about permutations. Okay. Because if you think about permutations, one way I could have thought about permutations was I have all 10 books, and let's just say I line them all up on my floor before they go on the shelf. Right? And then I put these 4 on the shelf, and then these 6 are going to go back into the box. Did I ever really care about the order of those 6? I didn't care about the order of those 6, so I divided by 6 factorial, right? And that's exactly what we did back. I mean, that's one way we could see that. Why did we divide? Anytime I divide by factorials, I'm saying order doesn't matter between, in this case, 6 things. Which 6 things? The 6 things that are going to go back into the box. Okay. So for the permutations, that's why we end up with this. We can think about it as lining everything up, and then the ones that we don't select, which are these 6, we divide by that number because we don't care about the order of those things anymore. When we first wrote this down as a multiplication principle, we're saying we do care about the order. And then what's happening over here with combinations, now I'm saying what? I don't care about the order of those things either. And so with my combinations, right, I divide by both 6 factorial and 4 factorial because I don't care about the order of the things that went back into the box, and I don't care about the order of the things that go up on the shelf. Okay. So they all ultimately break up into a multiplication principle question. It's just, exactly how do we want to think about such a thing. Yeah, we can go down lots of rabbit trails in terms of counting things, and we're going to stay semi-focused. We're not going to stay completely focused, but we're going to try to stay somewhat focused on the types of things that we count. So let's see. Let's go back to 20 U.S. edition, 24 international edition. I have a deck of 52 cards. Okay. And what's happening here, let's see, what's the probability that the 4 aces are all next to each other? So I have 52 cards. Let's see. I'm going to order, I'm going to cross out that combination. I'm going to order all the cards. So obviously, right, the question is if they're next to each other. By the way, we can think about it as combinations too, but it's probably going to make the most sense to think about it at the moment in terms of either a multiplication principle or a permutation. I'm going to order all the cards, right? And I want to know, I'm looking at the event in which 4 aces are next to each other. So, we'll count things first, and then we'll go ahead and we will compute a probability. So it does seem as though I want to think about this thing as order mattering. To think about this thing as order not mattering would mean that I don't care the order in which the cards appear, but somehow this seems to say I do care about such things. So, first order of business, I'm going to say at the moment order matters. probably the best way to think about this. Okay. I'll do a semi-variation off of this, maybe, and then we can see another. Well, I do an not exactly related but semi-related problem to this, in which we'll think about it the other way. Order mattered. I had to decide that to begin with. That's what I'm going to do, which means that I'm going to put these 52 cards together, and then I have all of these slots, right? There's some card that's going to go here, and a card, right? Each of those slots. And then I'm asking the question, what's the probability that there's 4 aces next to each other? Okay. So, let's see, what else could possibly happen here? Well, let's count this. Let's first say, what are the number of things in the sample space? Okay, when I perform this experiment, which is to order the cards, how many different ways could that happen?
52 factorial.
52 factorial. Right? 52, 51, 50, right? And again, I'm not assuming I put a card down and then pick it back up, right? Record it and put it back in and so on and so forth. I'm just putting it down. 52 factorial, or because I've decided order matters, I have these 52 cards and I want to select 52 of them in which order matters, which would give me the same thing. By the way, this would be 52 factorial over 52 minus 52 factorial. 52 factorial over 0 factorial. By definition, 0 factorial is equal to 1. Okay. Right. Just because there isn't a 0, no, we just say it's 1. Okay. It needs to, right? If it's going to make sense in this context, it has to be equal to 1. Okay. On the other hand, you can say, I'm going to start at 0 and count down until I get to 1, you'll never get there, right? So we have to do something else with 0, and we'll just call it. Okay? How many ways can I order nothing? 1 way, when I don't order anything, right? So I get the same answer there. So that's the number of things in the sample space. Okay. Now, I'm going to call this event A, is the event where the 4 aces appear. The number of ways in which that event occurs. All right, so how do we count those?
It would be 4 factorial, right? Because you're just lining up 4 objects.
Okay, so I could think of it this way, right? These could be my 4 aces. And I've already said order matters. So the ace of clubs would be different than the ace of hearts, would be different than the ace of spades, would be different than the ace of diamonds. And so how many choices do I have for the first ace? 4, 3, 2, and 1. But what's the experiment? I'm going to order all the cards. So now I have to ask myself, how many choices do I have for this position?
48.
48, right? These are aces, and then I'll call those ends. Those are the not aces. Not, right? The rest of them are the not aces. Okay. And then there would be 48, and 47, and 46, and 45, all the way down until I get the last one ordered. Okay. So it seems as though, we're not done by the way, we have these 4 factorial ways of ordering the aces, and then we have these 48 factorial ways of organizing or organizing the not aces. Okay. Now this was a specific example, right? This was one instance, right, of ordering those aces, in particular in the first 4 slots. But other things could have happened, right? What else could have happened?
The aces could have been like farther down.
Yes. The aces could have been here, and then the not ace and the rest of them. Or the aces, the only thing I know is the aces had to be next to each other, right? And so now the question is, and all of those are distinct, right? If the aces are in the first 4 spots versus the aces being in the 2nd through 5th spot, right? You know, right, so on and so forth. all the way down to the aces being in the last 4 spots. Right? Those are all different situations. How many different ways, but they're all going to be calculated the same way, right? And what would change if the aces were in these 4 spots? I'd have my 4, 3, 2, 1 here. I'd have my 48 over here, and then this would be 47 all the way down, right? I'd still end up with a 4 factorial times a 48 factorial. It would just be everything with shift 1. It would be a different circumstance, a different instance in which that was going to happen. Okay. So now the question is, how many different ways can I move those aces around? What's that?
49.
49, let's see, so if I start with 49, 50, 51, 52, that would take off the last. So I could start with the first ace could appear in the first spot, the second spot, all the way down to the 49th spot, right? If the first ace appears in the 50th spot, that's impossible unless your deck isn't fair, right? It's not, right, so there are 49. Every time I sort of set one of these up, there are 4 factorial times 48 factorial ways of thinking about it. But now there are 49 different ways in which we could reorder those aces. And that would be the number of ways in which it could occur. And by the way, these are both pretty darn big numbers, right? 52 factorial, right? 52 times 51, right? I'm sure if I plug it into my calculator, it's going to give me an error. A lot of calculators, right, they won't go that far up. Those are pretty big numbers, right? But the point is, if we go back to the original question here, the number of ways that we can order the cards in a deck, that's a huge number. The number of ways in which 4 aces appear together, that's a huge number. Does that mean it's really likely the 4 aces are going to appear together? No, it's only important relative to each other. So the probability of A, oftentimes we'll write it as, well, it's going to be the number of ways in which A could occur divided by the number of things in the sample space. Okay, right? We talked about it last time. Probabilities are going to be numbers between 0 and 1. That's going to tell me the likelihood. 1 is certainty, 0 is impossibility. It doesn't happen, right? So 0 doesn't happen, 1 certainly happens, everything in between is, some other likelihood. 1/2 is what we call a 50-50 chance, and so on and so forth. So when it comes to probability, it's not that this is a huge number, and this is a huge number, it's the relationship of those two numbers with each other in terms of a ratio. And this is going to be, I don't know what it is, right, off the top of my head, but let's just call it very small. And in fact, why is it very small, right? Because the denominator is 52 factorial, and the numerator is 49 times 4 factorial times 48 factorial. Is what we would get out of that, okay? And we can simplify this, right? We know, let's see, 48 is going to be 1 through 48 multiplied together. This is 1 through 52 multiplied together. Those will cancel out with a lot of those, leaving the 52 times 51 times 50 times 49 in the denominator. We can get pretty far towards answering this question. There's still a 49 here, and there's a 49 up here, so I'll just cancel those two things out. This is a 4 factorial, which is 24. So essentially the answer is 24 divided by 52 times 51 times 50. Okay. 50 times 51 is about on the order of 2,500, right? 2,000, I guess, 550. And then those two divided together is close to another 2 in the denominator if I cancel out. So this is close to 1 over 5,000. Okay. If I did my arithmetic correctly. Which you should check me, right? When you're dealing with factorials, don't just start plugging factorials in your calculator unless the numbers are fairly small like this. You need to clean them up first. Otherwise, your calculator is going to spit out error at you because the numbers get too big in a hurry. Okay? But essentially, this is saying what in terms of a probability that if you were to shuffle your deck completely into some random order, about every 5,000 times, if I if I got all of those numbers right, approximately every 5,000 times you do this, you will end up with 4 aces in a row. So if anyone has time this weekend, you can try it out. The better thing, and actually, we're not going to use the computer today, but we are going to use, I'm going to put some directions on Blackboard in the not too distant future. There's a lot of software out there, but there's software called R. And we will use it on occasion this semester. It helps us with try to understand probabilities. Because if we want to run an experiment where we try to do these things, we could actually run an experiment using R where we order them and we look at the likelihood of these 4 things lining up all together, and we could count and we could see, oh yeah, approximately every 5,000 times we do this, one of the times has those things in order, right? It's nice to actually be able to see. Nobody wants to sit in their room and well, maybe you do, shuffle your cards 5,000 times and see what happens. And then when you get through 5,000 and you don't get it to happen, you're like, what? I just wasted all this time. It's just like doing the birthday problem and you guys mess up the birthdays, it just happens. It's a little anticlimactic. So anyway, we decided to order numbers there. Okay, does that matter? Does that make sense? This is the hardest question with all of these counting, and we can go down so many different directions. It's the first question we always have to answer is, do I obviously care about order versus do I not care about order? Let me give you another question. It's going to somewhat seem like a variation it is a variation off of this, but we'll make it a little simpler. I'll say how you could set it up in that context. Okay. So here's my experiment. Okay. I will flip a coin 8 times. And I'll record what happened, right? So I'm going to flip the coin 8 times, and I'm going to record what happened. And I'm going to have these different events. Let me call it H sub 0 will be the event in which there is no heads in it. And H sub 1 will be the event in which exactly an head occurs, right? And H sub 2 will be the situation or will be the event in which exactly 2 heads occur. And so on and so forth, right? We could do that all the way down to all 8 of them. Let's compute, ultimately we're going to compute the probability each of these things occur, right? But to do that, we just need to figure out how to count things, okay? So I need to know the number of ways in which I can flip a coin 8 times, and the total possible outcomes, what are the number of things in the sample space, and then I'll compare that to the number of things in H0, the number of things in H1, the number of things in H2, and so on and so forth. Okay, so we'll put this counting into another example. Just put it into the counting into a probability question. And the first question is always, what's my experiment, and how many possible outcomes are there in the sample space? So if I flip a coin 8 times, what is the probability, or what's the number of things in the sample space? Yeah, go ahead.
2 to the 8.
2 to the 8. And this is strictly a multiplication principle, right? There were 2 choices, 2, right? Heads or tails, heads or tails, heads or tails. We're going to assume that it cannot land on its side and give us neither, right? It's just heads or tails. Everything is going to be heads or tails. And there's 2 times 2 times 2 times 2 times 2, right? Ways of thinking about this. Okay? How many ways could I get no heads?
Would it be one way?
The only way is if they're all tails, right? Tail here, tail, 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 tail. That's the only way to get no heads when we flip a coin 8 times. Right? And how many different ways could I get tail on the first flip? Tail is tail, right? One, right? One way, right? Here we had a choice, right? It was heads or tails, right? That's why we have these two. But here it's just tails. There's just one way of that. That's the only way. And multiplication principle says it would be 1 times 1, right? Be 1. So if you flip a fair coin 8 times, right? And what does it mean for a fair coin? A fair coin means it's equally likely heads or tails, and that's important because when we do something like this with probabilities, and we say the probability of A is the number of 8 ways in which A could occur divided by the number of things in the sample space, we're assuming everything in the sample space is equally likely. Okay? That we've set this thing up that, the fact that I, get ace, 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 and whatever is exactly the same likelihood as if those aces are somehow spaced apart with a particular outcome, right? So, sample space, everything in the sample space equally likely. And that wouldn't happen with an unfair coin, right? If I had a coin that flipped heads 3/4 of the times and tail 1/4 of the time, then I would be much more likely, let's see what I say, heads 3/4 and tails, I'd be much more likely to get heads all the way through than tails, right? They just wouldn't give me the same probability there. Okay? But with a fair coin, I just think it's equally likely to get it, even when I do it 8 times. So the probability then under that assumption that we have a fair coin would be 1 divided by 2 to the 8, okay? Which is a reasonably small number, right? Wouldn't happen all that often, right? So how many ways are there, put this in yellow, of getting heads exactly once when we flip a fair coin, or flip any coin in that matter, 8 times? Yes?
Wouldn't it be 8 times?
8 times, yep. Okay. Right? Because the heads could be in any one of the 8 flips. Right? I'm going to come back to this, but how about if I flip a coin 8 times? What's the probability I'll get heads exactly 2 times? It's 28, of course, right? Right? This is why we want to count, by the way, because I could write all the situations down, but I certainly don't want to, right? Because I know that there are 2 to the 8 different ways, different things in the sample space, and then this would be an event which I'm going to claim at the moment, and I have 4 minutes where we'll justify this claim. I'm going to claim that there are 28 things in that sample space out of that 2 to the 8, which correspond to heads appearing exactly 2 times, which would be tails appearing exactly 6 times. And we want to be able to do that. We want to be able to count those things without having to write down the entire sample space. In the same way here, right? These numbers were that much larger. We wouldn't want to write down the 52 factorial different ways that we could order these cards and then try to figure out which of those specific cases correspond to 4 aces in a row. No, we wanted to count those things in some way without having to write everything down. So it's the same thing here. So if I go back to this one, let's try to make sense out of this, and then we can make sense out of this. Okay. That what we had is, how do I end up with exactly 1 head? Well, there's my 8 flips. what can I do? Well, let me look at one instance, right? Heads could be here, and then these could all be tails. Now, this isn't the only thing that could happen, but that's one of the things that could happen. Right? And so then, let's see, heads here, tail, 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 tail. Okay? So then I have, how many choices how many outcomes give me this heads? One, yeah. And there's only one way to flip a coin and get heads. And there's one way to get a tails, right? Right? The only time this was a number other than one is when I didn't know if it was going to be heads or tails, right? So if you want a similar question but not quite the same, we could be rolling a six-sided die right now instead of flipping a coin, right? And let's say I'm asking for a 6 versus not a 6, right? Then there was one way to get a 6, and there are 5 ways to get a not a 6, right? And then 5 ways to get not 6, right? So they don't have to be ones, but just because there's one head, one tail, that's it. That's why those numbers are all 1. We could draw cards. I mean, the similar thing could be, I have these 52 cards, I could draw one off the deck, I could shuffle it back up, and I could draw one off the deck, right? And then I would have the difference between an ace and a not ace would be a 1 versus a 51, right? All right, so let's get that, right? We have one particular instance in which I'm in this setting, and there's one way to get the H, T, 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 T all the way through. Now, how many other ways are there of getting heads exactly once? Well, this H could go here, or it could go here, or remember the word or usually means addition, right? Or usually means, but nice thing here is the or is exactly the same, right? Because if my H goes here and my T goes here, it's still a bunch of ones. Okay? So in fact, what I have is, I have these 8 positions here, and I just need to choose one of them to be the heads. And so, I mean, how many ways are that to happen? There are 8 ways, places I could put that H. The other way I can think about it is there are 8 choose 1, right? I have these 8 slots, I just need to choose one of them to be heads, and that's also going to get me 8. That's the type, I mean, that's a very common type of combination calculation that we need to do. And so what's different down here? Let me just, because there's a lot of different ways in which there could be, there are 28 of them, I claim, had H, H, T, 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 right? And there would be 1, 1, 1, 1, right? I'm being very specific on what I want each roll to be here. But now, so there's only one way to do this. But now I have these 8 spots here, and I want to choose 2 of them to be those flips that ended up in heads. Order doesn't matter, why? Because, you know, I'm not calling this heads 1, heads 2, right? And that's different than heads. I just want to know the spots they are in for this. And if I do that, 8 choose 2 times 1, well, 8 choose 2 is just 8 times 7 divided by 2 is 56 divided by 2 is 28. And if you want to, you can write them out. All the way from heads, all the rest of them tails, to, you know, all the heads, tails, heads, tails, right? So if you write them all down, you'll see there are 28 of those things. I don't recommend, but if you have free time on your hands, go ahead and do it. This, we'll end right here. This is a particular type of counting. This is a particular type of probability question that's called a binomial, that's attached to something called a binomial random variable. And this is very similar to this question of, okay, I'm going to go out and ask 900 people who they're going to vote for this presidential election, and I want to know, well, what's the probability that, you know, 400 of them tell me candidate A, right? Or how many ways it could 400 of them tell me candidate A versus candidate B, and I could go ahead and see, oh, well, it's going to probably have something to do with, I forget which numbers I used, 900, you know, 900 choose 400, and that's it. Okay. All right. Well, Well, stop there, I actually kept you a few minutes late. I may send out and put on Blackboard some additional homework questions, because we're gonna spend one more day counting, and then we're gonna sort of move on to some more follow-up discussions. Any questions?
How do you discuss this?
I know. I actually really like the
I am sleepy.
I really like the conditional variable.
Fact that you have coffee right now.